Okay, this is the second podcast to redox reactions, and what we're gonna do now is we are going to apply what we learned from the first podcast onto the second one by reviewing a little bit about net ionic equations and a little bit more about solutions. So if I ever give you a reaction like this and I ask you what is being oxidized, what's being reduced, you have to also consider that this is a solution, and we know it's a solution because we see here it's aqueous and this is a strong acid. We also realize that this is a strong electrolyte because it's ionic, it's going to dissolve, and a gas is going to form as a byproduct. So these guys are going to dissolve. So we have to write a net ionic equation. And once we have a net ionic equation, we could figure out what's being reduced and what's being oxidized. So that's exactly what we're going to do. We're going to separate this into its net ionic form. So as you could tell, magnesium is a solid, so it just remains as its elemental form. This is a strong acid, so it's going to separate into its separate ions, and we're going to form products. So Mg plus 2 aqueous plus 2 Cl negative aqueous plus H2 gas. We don't separate that because a gas doesn't separate. So now we're gonna eliminate the ones that are spectators, the ones that are equal on both sides, meaning that they don't react. And magnesium here is in a solid form, here it's in its ion form, so do not eliminate those. They're different. Even though they're the same element, one is a solid and one it's ion. They're very different, so you don't cancel those. 2H and H2, different, very different. And these two are the same, 2Cl and 2Cl aqueous, okay? So what we're left with is MgS plus 2H plus aqueous, and that's going to make Mg plus 2 aqueous plus H2 gas, okay? Now that we have our net ionic equation, now we can figure out what's being oxidized and what's being reduced. Okay, so let me change the color here. Let's see how we do that. I forgot. Let's go to home. Home. Alright guys, be patient with me. This is my first time using this new program. I don't think it's working. Oh, there we go. What happened here? Okay, let's change it to red. Let's show the screen. Okay. So if we look at the sisters again, let's look at the sisters, family members. So this is magnesium. This is magnesium. This has an oxidation number of 0 because it's in its elemental form. It's bunch of Mg in a solid form. This guy's an ion, and we said that the charge is its oxidation number. So the number went from 0 to plus 2, so it's bigger, so this is oxidized, meaning that Mg is going to lose electrons, okay? It's going to lose electrons. It's going to lose 2 of them, right? Because it has a plus 2 charge. So it's going to lose 2 electrons. And the other one has to be reduced. And let's see if it is. It goes from plus 1 oxidation state. Don't look at the moles. Just look at the charge, plus 1. Each H plus has a plus 1 oxidation state. And this one's 0 because it's in its elemental form. So 1 and 0. That means that Hg is reduced, okay? So because the number goes down, So now we know what's oxidized, what's reduced. So Mg here, right here, is going to lose electrons to this guy, and then this guy is going to gain electrons to form this gas. Okay, okay, so that's what it is. Now I want you guys to try this next one. Go ahead and try the next one and see if you could figure it out without me. So find the net ionic equation and tell me if iron is oxidized or reduced, and explain using evidence. Your evidence will be your oxidation numbers. Okay, go ahead and do this, pause this, and try it on your notes, and then check your answers and use my explanations to guide you through the process. Okay, so you go ahead and pause and try. Okay, so let's do this. You guys looked at the equation and you noticed that it needs to be reformatted into its net ionic form. Solid would remain the same. FeS plus NiNO3 here. This is a polyatomic ion, has a -1 charge, and this would be +2 to balance out the charges. So -1 times 2 is 2. So what do you put here? You put a 2 and it's positive because it's a metal, or you could just crisscross backwards. This 2 goes up here. Okay, so can't forget about your charges. And we're assuming everything's balanced. Yes, everything's balanced. So now we separate this. It's going to be nickel +2 aqueous plus this guy right here, which is 2 NO3 aqueous, because there's 2 of them, 2 sets we put in the front. This guy's also separated. This is -1, 2, crisscross backwards. And get this 2, right? There's 2 crisscross backwards up there. And then that means you're going to have Fe +2 plus 2NO3. And this is a solid, so it just remains as a solid. Okay. And then you look at the equation before and after, and you see if there's anything that's the same, and only one is this one. Don't remove the Fe's because this one's ion form and this one's neutral. They're different, and then these guys are different as well because one is solid and one is aqueous. Okay, so when we rewrite it, we have our net ionic equation. And I'm just gonna rewrite it just so we could see it better. So you end up with this. This is your new equation, and now that we found our net ionic equation, right? That's one of our steps. We can now find which one is oxidized and what's reduced. So the question just specifies this one, but I'm going to do both. So as you could tell here, it went from an oxidation number of 0. So this is 0. Come on. 0 because it's in its elemental form, and this oxidation state would be the same as a charge. So it goes from 0 to 2. So it's going to be oxidized because the number gets bigger. And what that means is that Fe will lose electrons. Okay. And then if we look at it from the nickel point of view, here it's +2 oxidation state and 0 oxidation state. So the number gets smaller. So nickel, in this case, nickel is reduced. Okay, so nickel would be reduced in this case. So I'm not going to do this one, but just remember what we've been dealing with here are net ionic equations, and also most of these are single replacement. So just remember that if you see a reaction and it has aqueous, it needs to be separated and you need to eliminate the spectator. So just by looking at this one, we could tell that these chlorines here are going to be removed because they're going to be in their ion form, and they're going to be eliminated from the equation, and then eventually you'll end up with this. This is your net ionic, and then you could figure out what's being oxidized and what's being reduced. So if we look here, I'm going to do it again. Every time you do something like this, you turn it into its net ionic form, and then figure out the charges. So not the charge, the oxidation number. So this is 0 elemental form, this is +1 because of this charge, this is +2 because of the charge, and this would be 0 because it's in its elemental form, right? So if we look here, the calcium is being oxidized, so calcium is oxidized, while the H plus goes from 1 to 0, so H plus would be reduced. Okay, so that's how you do it. So let's see. Go ahead and try to figure out this one on your own, and if you can't figure it out, then I'll help you with it. So here we're saying that you have aluminum and HBr, and that you're going to produce H2 as a product. Your job is to figure out what's missing from the product side and balance the equation. Once you have your balanced equation, separate it so that it forms its ions, and that's going to be your ionic equation, and then get rid of the spectators, and that's going to be your net ionic, and then figure out what's oxidized and what's being reduced. And if you guys could do that, then you're pretty much set. Ready, set, go. Okay, so based on the question, it says that you have aluminum, and we're gonna assume that it's gonna be in its solid form, and because it's a metal, and then you're gonna have HBr, Br, and because it's an acid, it's a strong electrolyte, we're gonna say it's aqueous, and it's going to form H2 gas because that's what it says. It's going to form H2 gas. And what's missing is the aluminum and the bromine. So we're going to assume it's a single replacement reaction, and we're going to form AlBr. Then you look at the charges to see if it makes sense. So this is +1, this is -1, this is +3, this is -1. This doesn't balance, so you crisscross and you get this. We're going to assume this is aqueous. Because it's ionic, it's a strong electrolyte, so it's going to dissolve. And you look to see if it's balanced, and it's not. So what we do is there's 2 hydrogens here, so you put a 2 there. There's 2 bromines here, and there's 3 bromines there. So I told you when there's 2 and 3, you make the odd one even by multiplying it by 2. So there's 6 bromines. So how do we get 6 here? We're going to replace this with a 6, and we get 6 hydrogens, so we put a 3 here. There's 2 aluminum, so we put a 2 there. So that's going to be your balanced equation. Your ionic just means that it's going to be separated where it needs to be separated. So solid means no separation. Here it's aqueous, so it's going to separate. So you're going to have 6H plus aqueous plus 6Br negative aqueous. And then here you're going to form 3 hydrogen gas molecules. And you're going to have 2 aluminums and 3 bromines that form. This is aqueous, this is aqueous. So this is my ionic equation, and then my net ionic equation will be getting rid of the spectators, which in this case would be the Brs. Okay, so whatever is left, that's going to be your net ionic equation. Okay. And now that we have our net ionic equation, we could find the oxidation number. So aluminum is an elemental form, so it's 0. This is